Chapter 2, Section 2 on algebraic thinking. In this section, I want you to think about the following questions as you read through the material and study. I want you to think about, what does it mean to say that two sets are functionally related? What are some examples of functions in everyday life? Can we have functions without numbers? And what is the reason for developing algebraic thinking in elementary school? Consider those things and ponder them as you go through the material for this section. Standard 2 of the NCTM Content Standards talks about algebra and algebraic thinking. So make sure you read through those so that you get an idea of what the expectations are for elementary students when it comes to algebraic thinking, because there are a lot of topics and items there that students should be able to do. And so as an elementary school teacher, you may think, I'm not going to be teaching much in algebra, but the preliminary behaviors that go along with supporting fundamental algebraic concepts start now. Analyzing patterns, in fact, is one of the very first activities that students will engage in elementary school. All of you are probably familiar with this little picture that you see at the bottom of the slide, where students have to complete a pattern based on whatever shapes are present. The patterns may also include things like animals, colors, all different kinds of objects. They start these even in preschool and the kindergarten level. So even a fundamental activity such as this is the beginning of algebraic thinking. So when it comes to learning algebra, a lot of people think it's really kind of Greek. They think about it as another language. It can be a little bit confusing for some people. But honestly, the procedures and processes that you go through in algebra are all the same as fundamental basic mathematics. The only thing that changes is the representation that we use for the numbers. So while you may see things like letters and new symbols, the overall processes are going to stay the same. So don't allow those new symbols and variables to confuse you or throw you off. They're just meant to represent a generalized process, and we're going to talk more about that in just a moment. The first thing you're going to encounter when you're talking about algebra is the concept of variables. And a variable is just what it sounds like. It is an amount that is able to vary. In other words, it's an amount that's able to change. It doesn't have to be the same representative number or value every time. It's something that you can use, usually it's a letter, that you can use to represent any kind of given concept that might have a different meaning in a different context. You can see in these formulas below that there are numerous variables present, but in each one of those it means something slightly different, and that's okay. What we're using it for is to connotate all those different meanings, and that's the beauty and the flexibility that comes along with using those as a signature statement. This table illustrates the different meanings of the variables in those previous examples. In the first one, it's meant to represent certain quantities, like c equals pi times d. The c represents the circumference of a circle, and d the diameter. Those are exact amounts that you're going to get whenever you're looking at a circle, and so you're going to plug those in. In the next one, however, the x represents an unknown. We can solve for this unknown in this particular situation, but it's representing an amount that could change. We don't know for sure what it is when we start out. In the next equation or example, where we've got sine of x equals cosine of x times tangent of x, what the purpose there of the variable is to illustrate part of an identity property. And then as we go on through the last two examples, we see it continuing to serve the purpose of generalizing a property or a formula. So, when it comes to the next piece, when we're talking about not just variables, but we're also talking about the equal sign and uses of the equal sign, what do you think of when you see a problem like this? 6 plus 5 equals blank. Do you automatically think, oh, there's an equal sign, so I have to solve this and get the answer? If so, that is a misconception that you're going to have to modify before you begin teaching algebraic concepts of things like the equal sign to students in the classroom. That equal sign is not actually a get the answer kind of function. What it is it illustrates the connection between what's on the left side and what's on the right side. It is in fact a relational symbol, not a computational symbol. So students need to understand that when they see that equal sign, it doesn't mean get an answer. What it means is what is on one side is equivalent to what is on the other side. So it could be an 11 in this case, or It could be 6 plus 5, which is an equivalent expression, because we know that if we switch the numbers around in an addition problem, we get the same amount. It could be any number of things. It could be another combination of this. It could be 2 plus 4 plus 5. The point is, it means and indicates a relationship. So get used to saying that the equal sign actually represents equivalencies. We use a lot of algebraic notation to denote the structures, and some of these include just different properties for the operations that we have. One of the properties that I just mentioned earlier is the commutative property. That's where we can move the numbers around and still get the same answer. That is true for addition and multiplication. There are other properties as well. The closure property, associative property. You may not be familiar with all of those off the top of your head, but the same things apply in algebra as in regular mathematics. So when we talk also about even numbers or odd numbers, we can represent those with an algebraic representation. Every other number is even, so we're going to be adding 1 or adding 2 each time to get the next consecutive number depending on what we're looking for. And we can even show different connections between operations, like when we are combining integers. A minus b, we can represent that as a plus a negative b and still show the same connection between those values. So it's very important that we keep in mind that algebra just gives us another avenue for showing these structures in a more generalized way. So since relationships often exist between different variables, we can use those in a certain way to develop a representation of a function that we're looking at or a computation that we're looking at. For example, when we look at the area of a rectangle compared to the length and width, we know that if we take the length times the width, we get the area. We could write that out as a function of something, or we could write that out just as a simple equation, but we can show that relationship between the variables with the equal sign. So patterns and relationships can be represented in a lot of different ways. We can talk about them, we can draw them, we can graph them, and use numeric and computational symbols to represent them as well. The point is being able to communicate very clearly the patterns that you see within a problem is very, very important. So you heard me use this word function already, and you've probably already heard of it before, but basically all a function is a relationship between two sets. So you've got a set called the domain, and that's your input values. Those are the values that you would put into some kind of process, and then the numbers that you would get out as a result of that process would be the range. Formally defined, it's a relationship between two sets where every element of the first set is matched with exactly one element of the second set. So what we're doing here is we're taking a look at putting numbers in, getting numbers out. A lot of times you see this represented as a machine. Teachers kind of convey that, where you've got a number that you stick into the machine and you do something to it and you get a number out. And kids can play a game with this where they try to figure out what the operations are that are being done to it. Maybe it's something as simple as adding a number, like adding 1 to it, or dividing it by 2, or something like that. It doesn't have to be complicated, but a function is something that's being done to that number. Now, just because two different sets of items are related doesn't mean that they're functions, so think about this for a minute. The relationship between the set of positive whole numbers and their square roots. So when we put a number in, we want to get one matching number out, okay? Not two. So if we think about whole numbers and their square roots, like the number 9, if we were to take the square root of 9, we would get a positive 3 and a negative 3 as a possibility. Think about that for a minute. Positive 3 times positive 3 is positive 9. Negative 3 times negative 3 is positive 9 as well. So while those are related, they are not functions because we get two values for the one number. So the square root of 9 could give us two values, positive 3 and negative 3. That means it's not a function because we shouldn't be getting two values, only one. Besides writing functions as an equation like y equals x plus 3 or whatever, we can also use something called function notation. And what that is simply kind of a curvy letter x or F, excuse me, or italicized, with an X in parentheses, showing that X is our input value and we are performing some kind of function on that X. So here, for adding 3 to a number, we've got f of x equals x plus 3. So if we were to take the number 2 as an input value, so 2 is our x, or our domain, we would put it into the function, and it would say f of 2 equals 2 plus 3. And then the final value, or the range, for that domain of 2 that we put in would be 5. So function notation is more precise because it really tells you exactly what's happening. And you can see here an example of that. If we were to use that previous description where we're adding 3 in that function, and we're placing in values of 3, 4, and 10, and getting out values of 6, 7, and 13, it really shows you what's happening. So take a look at these graphs below, or graphics, I should say. In this chart, we've got the input values of 1, 2, and 3, and the output values of 4, 7, and 10. So if you think about this, what is happening to those numbers? When we put the 3 into the machine, or put the 1 into a machine and get a 4 out, something's going on. Likewise, if we put the 3 in and get a 10 out, what do you think's happening? Well, could be what's happening is we're tripling the number and adding 1. So let's see if that holds true. If we put a 1 in, 1 times 3 is 3, plus 1 is 4. Put a 2 in. 2 times 3 is 6, plus 1 is 7. That works every time. So in everyday English, you can just say that the rule or the function is to triple the input and add a 1 to it. That's not the only way we can represent this function, though. We can also make a table that represents our amounts. We can develop equations. We can make charts. We have many different options for representing functions. Here you can see a demonstration of a graph where we can represent a function. So in this particular graph, we've got hours compared to dollars. So that sounds like a wage problem to me. Based on the notation here in the slide, they're talking about babysitting. So what you can do is you can refer to the input as the independent variable, in other words, the number of hours worked, and then the output, or the money that that person is making based on the hours worked, is the dependent variable. Why? Because it's dependent on how many hours the person works, or how many hours they babysit. We can also look at these relationships as a set of ordered pairs, where if you put the number in, like 1, you get an 8 out. So we can write that as an ordered pair, input 1, output 8, or domain 1, range 8. And in fact, later on in algebra, they will start doing it that way and looking at those as domains and ranges in ordered pairs. Or we could show a mapping, where we've more or less got a table, but we just show an arrow representing the fact that if we put a 1 in, we get an 8 out. So up to now, we've talked a lot about representing information in a variety of ways. One of the ways in which we can do that is by modeling things mathematically. Now that doesn't mean just making pictures though, okay? It's more about making things realistic so that we can solve a problem, because real life problems are messy. They're not clean cut. We have to approach them from different avenues. There sometimes isn't a clear cut answer even in a real life problem. So the NCTM wants to make sure that mathematical modeling is included in mathematics education in school. So remember that a model of an object is not the actual object. It's usually something that's scaled down. You can think a lot about a model airplane or a model car, things like that. So when you're building something big and important, you always start with a model first. You never do the real thing the first time out. You build a model first, you test it, you take a look at it, and you make sure things work. Mathematical models are very much like that, in that they are an approximation of the situation. So that could be an equation or a set of equations. It could be a graph that models whatever the behavior is of the different topics within a problem. Or it could be a Venn diagram, or any kind of a graph that shows or illustrates what's happening within the context of this problem that you're looking at. Let's take a look at some examples of mathematical models here. We've got this student, Rageb, who is running a race, okay? He started quickly, but then he stopped to tie his shoe. And then, after he tied his shoe, he was able to run even faster than before. We've got a representation of three different graphs here showing time compared to distance. So when we're looking at these graphs, which one of these do you think most closely reflects his speed and activity? Keep in mind that a slower speed is going to have a smaller slope. In other words, it's not going to go up as steeply as a faster speed. And stopping means that the person is not going to get any closer to the finish line. So what do you think? Well, the first graph is the best representation of his activity. You can see he's running pretty quickly, but then he stops. And so this horizontal bar shows he has not made any progression towards the end of the line. So the distance is not increasing, but time is continuing to go and move. Okay, so the clock's still running even though he stopped. Then he runs even faster than he did when he started out. So which of the graphs below represent this scenario? A runner is running at a steady rate and then comes to a hill, which causes her to run at a slower rate. Once she reaches the hill, she runs down very fast. Upon reaching the bottom, she resumes her original pace. What do you think? The default is typically this first one, right? Because you think, okay, she's running up a hill, so there needs to be a hill in my graph. That's incorrect thinking. Look at the units here. We're looking at time compared to speed. So if somebody is running and they start running up a hill, are they going to go faster? No, they're going to go slower. So their speed is going to drop until they reach the top of the hill where their speed will be the slowest. And then their speed will start increasing as they go back down the hill. So the second graph is actually the representation of this problem and the mathematical model that we want to use. So it's important that we teach kids how to use algebra to generalize different arithmetic and mathematical processes, because being able to recognize and use patterns is really going to help them solve problems later on. And remember what I said, patterns are the fundamental basis of algebraic thinking in elementary school. Okay? So just because kids work with patterns alone, though, doesn't mean they're going to build algebraic reasoning. It's a big step forward, though, in helping to prompt that. When we move forward with analyzing those patterns to making generalizations and working with functions and everything else, we'll start to build that piece of algebraic thinking that they're going to need as a foundation later on.